Hey guys, welcome to the Tuesday Tune. My name's Steve, run Vorsprung up here in Whistler, and this week we're going to run you through a very commonly asked about topic, which is the way that shim stacks function. So many of you are aware that a lot of mountain bike suspension dampers run shim stacks to control oil flow in both compression and rebound. So the job of the damper is essentially to slow down the motion of the fork or the shock. The way that that's done, as we've discussed in previous videos, is by forcing oil through small gaps, essentially. The way that the aperture size is controlled, so the aperture size being the flow area that the oil has, is very important in terms of determining the performance of the fork or the shock's damper. One of the most common ways in which we control that flow area is using a shim stack. So a lot of people out there are already messing with their own shim stacks, tuning their own forks and shocks, or trying to. What we're going to go through is the fundamentals of how the shim stack actually functions, what various changes will do, and some of the things that you need to be aware of if you're going to try to revalve your own fork or shock. So this is a pretty typical shimmed valve configuration. This is out of a very old Marzocchi Rocco, actually, one of the many shocks that we have in our graveyard here. So this is the compression piston, or the main piston I should say. It's compression and rebound piston. As you can see, this one is pretty scarred up. You'll notice it has three very large ports and three smaller ones. The smaller ones are the rebound ports. If you can see on this side of the piston here that it is it's kind of dished there, which preloads the shims on the rebound side. On the compression side, this face is flat and these shims sit flat against it there. So we have the rebound shims. We have a check valve here to make sure nothing is going through the rebound circuit, like the low speed rebound circuit, backwards. So these rebound shims cover the ports there, like so. And then we have this shim stack here, and that covers the compression ports. So when the shock is compressing, the piston is moving in that direction, the oil is moving obviously in the other direction. And so oil is going into those very large kidney-shaped ports here, and it's flexing these shims up. So these shims are clamped at the back against the shaft. I don't have the shaft here to show you. I think it probably ended up in the bin years and years ago. So the way that oil is allowed through these ports is basically the flexing of these shims. They act like a leaf spring. So they are basically lifting up off the port like that, peeling up off the port. Now, as we've discussed before, the reason that shimmed valves are so popular is because they give you a way of very precisely controlling the effective spring rate of the valve, in that the valve, or the shims I should say, act like a leaf spring or a series of leaf springs that can allow oil to flow through with zero preload on the shim stack if necessary, or you can preload it if you would prefer a digressive curve. And what that means is that by changing out the shims here, by either adding or subtracting shims or changing the thickness or the diameter, we can effectively change the spring rate of the overall shim stack. So you may notice that this shim stack, not all the shims are the same diameter. The largest diameter ones are against the face, where they're sealing over the compression port slot there, and then there's a series of slightly smaller diameter ones. Now the reason for this is not that one shim controls higher or lower speeds. In reality, they all have an effect at basically all speeds. What this basically does is allow a very gradual flex, rather than having a very defined fulcrum or bending point at the clamp diameter. As the shims flex up, then it will allow that bending point to be slightly different for each shim, and that prevents breakage of the shims, basically fatigue of the shims. So that's the main reason why that is done. It also allows for more opening clearance of the shims because they'll usually have a backing plate behind them that sets the maximum distance that they can open. Other than that, characteristic-wise, there is not necessarily any difference between that and a straight shim stack where all the shims are the same diameter. So what we have here is a very basic force versus velocity plot for two linear damping characteristics. So this one here is a very arbitrary value. What you might get if these were, say, 0.1 millimeter thick shims in a what we call a straight shim stack. So all the shims here are the same outer diameter. This being the center line of the shaft, piston bolt up here. This is obviously the piston, and that being the flow path of the oil. So it's clamped with a certain diameter, certain clamping diameter down here, and that essentially provides the fulcrum, the pivot point, or the bending point around which the shims will flex. Now, if we have a straight stack like that, obviously all of them are going to try to bend directly above that clamping diameter. What that means is that it's common for them to end up fatiguing and breaking there if they have to bend a long way. If they don't have to bend very far, it doesn't necessarily matter. So let's say we make these shims 0.1 millimeter thick, and we have 5 of them there. That would give us this curve here. Now, if we were to then change those from 0.1 millimeter thick to 0.2 millimeter thick, then we end up with a gradient like this. So if this is a gradient of 1 to 1, this becomes a gradient of 8 to 1. A very effective way to make large changes to the stiffness of your shim stack and the amount of damping that you get out of it is to change the thickness of the shims. Now, this graph is not actually strictly technically correct if there is either a substantial low-speed bleed or this substantial viscous effects, which there are at low speeds either way. So these curves down in this region, the low-speed area, will usually deviate somewhere from there. This part will be accurate above a certain flow rate, basically. We can also substantially change the effective stiffness of the stack by reducing the amount of leverage that this port has over the clamping diameter. And obviously the way to do that is not to move the port, it's to shift the clamping diameter. So if we change this clamping diameter to come out to here, now this port, instead of having effectively from the center of pressure here to here as leverage, we only have that much leverage instead. And so obviously that means less bending moment on the shims, makes the shim stack effectively stiffer. So one of the simplest ways to play with the stiffness of your shim stack, especially if you're trying to increase it, is to increase that effective clamp diameter by using a thick shim at the back of the stack. That means that it's being clamped rigidly out further than where it was before. Trying to reduce that clamp diameter is not always possible. So if the configuration of your damper means that that clamp diameter is already at the minimum that it can practically be, for example in the RockShox charger dampers, there is nowhere to go down from that a lot of the time. In that case, we need to actually start reshuffling the shims. To illustrate a bit more about the way that the shim diameter affects its bending stiffness, which is really what we're looking at here. If we imagine that this red port here acting on the blue shim, so oil coming through the red port, trying to bend the shim, if this green dotted line is the clamp diameter, then it will basically bend along that black line. It'll bend in a two-dimensional fashion, basically. And so if you make this diameter larger on any of the shims, then basically you increase the length of that line and the amount of material that the oil pressure acting on the other side of the shim is actually having to bend up. And so that is why larger shims, or larger diameter shims, are effectively stiffer than smaller diameter shims as part of the stack. So where this is particularly useful is when you want to make relatively small changes to the stiffness of your shim stack. When we have a damper with both a base valve and a mid valve, so the base valve would be like the compression assembly in your fork, or generally the external compression adjustments on your shock, and a mid valve being your main piston on the shock, or in the case of the fork, it's usually the rebound piston check valve. So where we can kind of get ourselves into a bit of trouble if you're revalving stuff is if you revalve the main piston too heavily relative to the pressure drop generated by the base valve. So if we have pressure drop versus velocity curve here, this is our base valve pressure drop versus velocity. We basically need our mid valve on the main piston pressure drop versus velocity to be lower than that. And so lower or equal. If you manage to get it exactly equal, that is essentially what you would refer to as pressure balanced. If you end up with a pressure drop over your mid valve or your main piston that is larger than the base valve, then you're only relying on the back pressure of the shock, so the nitrogen pressure of a shock, or in the case of a fork, the pressure generated either by a bladder or a floating piston, so like the spring-backed IFP in some cartridges. However, if that pressure is not sufficient to force oil through the main piston at a high enough rate, then the shock will cavitate. This is why it is quite difficult for most people to revalve their own rear shocks if they're working on the main piston. There's also the fact that unless you're able to measure it, you really don't know how much of the damping force and what the pressure drop is coming from the main piston and how much is coming from the base valve. There are shocks out there where you could double the stiffness of the valving on the main piston and it will make absolutely zero perceptible difference to the ride quality. It will only make a difference of a couple of percent to the overall damping stiffness because the main piston is valved so lightly to begin with. And so in some cases like that, the manufacturer's specified, soft, medium or firm tunes are completely irrelevant in compression. In some cases they make a huge difference as well. So if we look at the amount of force that you can get out of, the amount of damping force you can get out of each of those valves, what becomes apparent is that you can actually get more damping force out of the mid valve or the main piston, typically, caveat to that in a second, than you can out of the base valve, because the area that the oil pressure is acting over is larger. So in the case of the base valve, the pressure that it exerts is only basically on this area here, so the diameter of the shaft. The main piston or mid valve pressure drop area is acting on the area of the piston, so the cross-sectional area of the bore minus the shaft. So typically, if this bore is more than 40% larger than the diameter of the shaft, then you are able to get more damping force out of this mid valve than you are out of the base valve before you start crossing that pressure balance equilibrium. So that is why we can often get a larger percentage of our damping force out of the mid valve than the base valve, even though the pressure drop across it is smaller, just because the area that pressure drop is acting on is much larger. For those of you, and I know there are a lot of people out there that love tinkering with this stuff, if you're going to start with revalving stuff, I suggest that you start with the base valve of a fork, because almost always that generates the majority of the damping force, even in a fork, because most of the mid valve configurations generate very little damping. They're essentially a check valve. So to avoid issues with cavitation and to make meaningful changes, start by playing around with the shim stacks in your fork. So in a Fox Fit cartridge, the RC2 cartridges are pretty nice to work with there, as are the RockShox charger dampers to a certain extent. They are a bit more complicated, the charger dampers, in that they use a preloaded Shimz setup. Anyway guys, I realise we've only scratched the surface of that one. There is obviously a lot to do with tuning shim stacks. Making the adjustments to the damper is actually the easy part. Working out what you need to do to the damper is the hard part. So working out, do you need more compression, do you need less compression, do you need more high speed, less high speed, more low speed, less low speed. And then the same deal with the rebound. That is really the most difficult part about suspension tuning. Anyway, that's it for this week's Tuesday tune. Next week will be our last Tuesday tune for this winter. We may continue them next winter, I have not decided yet. But anyway, until next week, I'll see you then.